Okay, welcome back to my channel, everyone. I am Ansar, your helping hand, and today we're going to be talking about the central limit theorem and how it's important and why it's important, basically. So, in order to understand the central limit theorem, we have to look at the limitations of our current sampling distributions that we have. So, in previous videos, we've come up with this framework around samples and data and, X in bars and S's and those kinds of things. And we've come up with the following results. So we have these things called statistics, right? Which, remember, is just a function of a random variable. Okay. Now, these particular statistics that we have are important because they have what are called pivotal distributions. And basically, the pivotal distributions are pivotal because the parameters of these distributions, right, here 0 and 1 and n minus 1, those parameters, right, they don't depend on any unknown value. 0 and 1, those are just constants. N minus 1, n is the sample size, and if we're doing a sampling distribution or we're doing a sample, we know what our sample size is. Again, we have n and then n minus 1 and n minus 2. Those are our two different samples. So these pivotal distributions are useful because essentially we can then use our pivotal distributions to make inferences about specific things in our statistics. So for instance, in this particular statistic, we have mu and sigma squared, or we have sigma, so the standard deviation rather than the variance. And so we can make inferences about mu and sigma because we have this pivotal distribution. We can calculate what the probability of seeing this particular value is, seeing this particular thing being equal to a certain value or between certain values, and it goes for the rest of the statistics as well. So that's kind of where we are up until this point. But now the issue or the limitation with this is that all of these statistics that we have, right, all of them and all of the results that we found using them, they are all predicated on the fact that we have normally distributed data. So remember in our first sampling distribution video, in part 1 of the sampling distribution videos, we saw that X in bar is normally distributed. But that only holds true if every single one of our observations that we had, or if our data that we had is normally distributed by itself. So the usefulness of this particular fact, we need to have normal data in order for that to be useful, because this only applied when we had normal data. We only proved it for normal data. And the same goes for all of the other results that we prove regarding like sample variance and the ratio of sample variances and things like that. So we had this normality assumption that our data was distributed normally, but in practice, your data can be distributed in so many different ways, right? You can have exponential data, you can have geometric data, you can have all kinds of weird and wonderful distributions that your data will follow, and we still want to be able to make inferences about that. So what about those sampling distributions? What happens if x1, x2, ... xn are some, let's say, beta, right, with an a and a b? We still want to make, inferences about what we think this a is, or what we think this b is, or what we think the sample mean is, or what we think the actual mean of the data is. And so in order for us to do that, we need to develop sampling distributions for each of these for all of these distributions, right? We need sampling distributions for them as well. Now, you could, in theory, go and, start the same kind of process of saying, okay, these are x1s, these are x2s, these are xn's, and do the same kinds of things that we did for the normal data. But the issue is that usually it won't work out nicely, and it won't work out in a way that is useful to you. So that's not the way we need to go. And instead, right, what we have is the central limit theorem. So the central limit theorem allows us to make inferences about data that's not normally distributed, and we'll see how it works. So the central limit theorem has certain assumptions about your data. So remember, these x1s, x2s, those are all observations, right? Observations of random variables. And the random variables that you're talking about have some particular distribution, and we're assuming that every single one of those random variables are identically distributed and they are independent of one another. There are versions of the central limit theorem that don't need independence or don't need identical distributions, but essentially those are not the kinds of central limit theorem cases that we'll deal with. So they're independent and they have the same distribution, and they have some mean mu and some variance sigma squared. I say finite here for both of them, and that just means that mu needs to be less than infinity and sigma squared needs to be less than infinity. And what that means is just that we can't have an infinite expected value and an infinite mean or an infinite variance. And for the majority of the cases that we work with, these assumptions are okay, right? But we need to stress that we have these assumptions. So if we can't meet these assumptions, using the central limit theorem is not a mathematically or statistically sound thing to do. And so if you base any decisions on using the central limit theorem and you don't meet these assumptions, you're making a mistake. And we saw in the example about ventilators and things like that, that sometimes those mistakes mean very serious things. So that's why I'm stressing the assumptions quite a bit. But anyway, if you meet these assumptions, which usually you do, the central limit theorem says the following. The central limit theorem says that the limit as n goes to infinity of this particular statistic, remember a statistic is a function of a random variable, and we can kind of call this the I think I'm spelling that incorrectly, but the standardized sample mean. Okay, so standardized just means you take away your mean and you divide by your standard deviation. That this particular statistic, once n goes to infinity, that is equal to a random variable that has a normal distribution, specifically a standard normal distribution. Now, the reason that this is important is because basically what it's saying is that as we increase our sample size, right, or in other words, as n gets larger and larger and larger, the sampling distribution of our sample mean, or xn bar, will look more like a normal distribution regardless of the original distribution of the data that we had. So breaking this down, right, what this is saying is that we can have data that's distributed in whatever distribution we want, right? As long as our data has a mean, and as long as our data has a variance, and that they're independent and they all have the same distribution, that when we take samples of a particular population that has that distribution, right, that the sample mean that we calculate, which is a random variable, that will have some normal distribution. And if we standardize it correctly, then we'll have a standard normal distribution. So essentially, because of that, because we've now shown that as n gets larger and larger and larger, or that the limit as n goes to infinity, that the sample mean, right, xn bar, has a normal distribution, we can then use all of the results of the previous chapter with regards to chi-squared distributions, with regards to t distributions, with regards to f distributions, to make inferences on data that's not normal, so long as our n, right, our sample size, this number of observations we have, as long as that is large enough, then our sample mean will be approximately normal. So all of the other kind of results about normal data will approximately hold. Now, I say approximately, and I'm stressing this because I want to kind of highlight the fact that the central limit theorem, right, doesn't say that once n gets to a particular number that this statistic is a normal distribution. It says that as n gets to infinity. So once this reaches the infinite limit right, then this particular statistic will be normally distributed. So only once we have an infinite sample size, only then will our actual statistic be equal to a normal distribution. However, the kind of implication about this limit is that as n gets larger, right, as we take bigger and bigger and bigger sample sizes, that this statistic, while it might not be exactly a normal distribution, it will get closer and closer and closer to a normal distribution. And once it gets to a certain level of closeness, we can either say for our particular field that we're working in that is okay. We are okay with that approximation. Okay, and the sample size that we need, right, depends on the distribution that you have for your original data. So, I mean, we'll get to that later, but essentially the size of n depends on what your original data looks like. And in most cases, n being greater than 30 will be sufficient. But once again, that does depend on what kind of data you have. Okay, so that's the central limit theorem in a nutshell. And you could technically stop this video right here or go on to the next second slide after the one that I'm about to do, because I'm going to go over sampling distributions again. And the reason I'm going to go over it is to explain what we mean by sample distributions, basically. And it's important in a way because it helps you see empirically why the central limit theorem holds. Now, I will have a proof for the central limit theorem on the channel. I'm not sure if the proof is necessary to know. The proof can be understood using all of the knowledge that we have up until this point in our lives with regards to math and statistics. And it will be a different proof to the one that's in the textbook because the textbook uses Taylor series, and we haven't done that in math yet, so it's a bit difficult to use those. The proof will just be based on MGFs and limits of MGFs. So you can go and check that out if you are interested, just to see why the central limit theorem holds. But essentially, you don't necessarily need to know the proof to understand why it's important. And the reason it's important is just that the central limit theorem allows us to make inferences about data that's not normal as long as we have large enough sample sizes. Okay, so before we kind of move on, I want to reiterate what a sampling distribution is through a very practical example. So suppose we have a population, right, that we're interested in, and let's say it's the heights of South African women over the age of 18. This is a population that has roughly 20.6 million heights, and we want to know the average height or the expected value of the height from this population. Now, every single height in the population is unknown because unless you know, 20 every single, like off the top of your head, unless you know 20.6 million numbers of the heights of 20.6 million women, every single height essentially is unknown in practice, right? We don't know what it is, and also it's not the exact same height. Not all women have the exact same height. Women's heights are variable, and so we're unsure or we're uncertain of if we take someone or if we take a particular person, right, we're unsure of their particular height, and so there's uncertainty in the value of that person's height. But what we can do, right, we can model the woman's height or a woman's height using a random variable. And we don't really need to know what the distribution is. We just need to say that, hey, this woman's height or women's height in general can be modeled using a random variable, and that's all we need to know. Now, if we're worried about, or if we're concerned or want to study the average height, right, of women, because we've now, used a random variable to model heights, the average height is equivalent to taking the expected value of the random variables, because the random variables are the heights and expected values are averages. Okay, so okay, Lord, I'm just gonna erase that so you can see what I've written. But now, if we think about the average height and we knew every single individual women if we knew all of their heights, right? Let's say we had a spreadsheet with 20.6 million numbers, and that was the height of every single woman in South Africa, then we could, right? We could find the average, and that calculation would be easy. You use a formula, you just add them all up and divide by 20.6 million, and that would be easy. But in practice, we can't do that. And so we need to go and measure women, and measuring 20.6 million women's heights is not easy. That's difficult. That's not an easy calculation. So instead, what we can do is we can sample, right? We can take a subset of the population and calculate the average height of the sample. Now, that would be the sample mean. So that would be our sample mean, xn bar. And what we're kind of implicitly assuming is that xn bar is somehow an estimate of what our actual population's average height is. Remember, we're concerned with the average height of the entire population. Now, the sample that we take, right, our sample, like who we pick in our sample matters. So, for instance, if I went to a modeling runway or a fashion runway, and I went to go and sample models' heights, right? We kind of assume in everyday parlance that models have very, very tall heights, and they're quite tall. So if we go and sample models, right, we're going to get a lot of tall women in our sample. So our sample mean is probably going to be higher than what our actual average height is. So that's what we mean when we say who we pick in our sample matters, or the actual sample, the values that we get, or the people that we go and sample matters. And then also how many people we're sampling matters as well. If we take a sample of 2 people, for instance, right, because I'm taking only 2 people, right, every single person in that sample contributes 50% to the average, or the sample average, right? So if I have an outlier, right, if by some random chance I have the tallest woman in South Africa, saying woman and women is sometimes confusing for me. But if we go and take, the tallest woman in South Africa, and we have, let's say, a normal heighted person, right, taking the sample average of 2 women is going to give us a sample height much bigger than what we actually think our average height is, because we've got the tallest woman. And the reason that the outlier, the tallest woman, affected our sample mean that much is because our sample size was only 2. If we take a sample of 50, right, that really, really tall woman is only going to contribute 1/50th of the total sample, or this total sample average that we calculate, right? So our sample size matters, because the more samples we take, right, the less likely outliers will affect that sample mean. And so the sample mean will be closer to the average, the actual population average, or the population mean. So in other words, our average height that we have, our sample mean, our xn bar, right, the value of that sample mean also has uncertainty, just like the original heights that we had. But the uncertainty is a different kind of uncertainty, and it comes from different places. The uncertainty for our original data comes from the fact that we don't know what women's heights are, and that women's heights can be different numbers naturally, right? The randomness or the uncertainty from our sample mean comes from who we actually pick, who's in our sample, and how many people we sample, right? So that's why we say that the sample mean, or the sample average, right, the sample average, that is a random variable. So because it's a random variable, it has a distribution. All random variables have distributions that tell you what the likelihood of seeing a particular value is. And so we can go and find that distribution analytically, which is what we did in chapter 6 and in chapter 7.1 and 7.2, what we did in the previous videos. We can go and do that analytically using maths and using MGFs or distribution functions and things like that, right? Or what we can do is we can go and do it empirically. We can go out and we can sample many, many times. So we can, let's say, and it has to be the same size, but we can, for instance, go and say, okay, cool, we're going to sample 50 women, and we're going to sample 50 women today. The first 50 women that, let's say, walks through the Nilsi, right, at one particular entrance, and we sample their height, we measure their heights, and we calculate the average, and then we're going to do it again tomorrow, and the following day, and the following day, and the following day, and we do that for an entire year, right? So then we have 365 different sample heights. And remember, the reason that they're different is because our sample height, our sample mean, x in bar, that is a random variable. It can take on different amounts. And then we can create a histogram for our 365 sample heights that we have. And histograms are basically measures of relative frequency, and relative frequency is approximately probabilities. So, you know, that's kind of a recall week one descriptive statistics things, but essentially, when we go out and we repeatedly sample things, right, we then create a distribution for our sample mean, and we can look at that particular distribution, the empirical distribution, and say, okay, we can see that we kind of got the majority of our values between these two numbers, and so maybe we'll say that our actual population average lies in that interval as well. So now, because we've created a histogram, right, that particular histogram no longer depends on who is in the sample, because that's kind of what the histogram's trying to eliminate, because we don't really want to think about the randomness of, we don't want to think about the randomness of a particular sample based on who's in the sample, because that's what the histogram is trying to eliminate. By taking multiple samples, you're trying to go, okay, one day my sample height can be this, another day my sample height can be this value, and the next day it's that value. And by creating the histogram, you're saying, okay, if we're trying to eliminate all of the not all the randomness, but the randomness that's associated with the actual sample, as in who is in our sample, the histogram tries to eliminate that. But the histogram, or the distribution that you get, will depend on the sample size once again, because it's the same idea. If you take two people, if you sample twice, right, even if you sample multiple times, you can still get weird looking data or biased data. So the histogram doesn't eliminate the sample size uncertainty, but it does eliminate the actual sample randomness. And so what the central limit theorem says is that as you go out and you increase the size of your sample, that the histogram that you get when you repeatedly sample things, that will look like a normal distribution, or it will look like a normal histogram, where the majority of the data lies in the middle and then very little data lies in the extremes. Okay, so that was the sampling distribution kind of recap. That's important to understand why the central limit theorem works, or what it looks like, or why it's important. I'm now going to do a kind of another example that you can actually see what the histograms look like. And that's the dye example. But before we get to it, there's kind of some mathematical legwork that we need to do. So remember that the central limit theorem says that this particular value, and I don't put the limits here because, one, I didn't want to write it out multiple times, but also there's another reason that I'll explain later. So I just put it over the tilde sign. And what I mean by that is I'm just saying that as n goes to infinity, this particular statistic looks like a normal distribution, or has a normal distribution. So what we're saying there is that this particular statistic has a standard normal. And remember, the way we standardize is we take our x value and we subtract our mean and we divide by our standard deviation. And in this case, our standard deviation is, well, that's a whole that's a whole question about what the standard deviation is. But essentially, what we can then do is we can kind of unstandardize it. So this is z, right? This is the standard normal. We can unstandardize it by essentially multiplying it out and adding the mean back in to get our original data. And what that does is we then just get our x in bar, right? And this, once again, as n goes to infinity, says that x in bar, our actual sample mean, right? our actual sample mean will still be a normal, right, in the infinite case or in the infinite limit, where the mean value, right, that the sample mean will take on is the same mean as our original data, but our variation, our variance, will no longer just be sigma squared, it will be sigma squared over n. And if you think about this, right, I explained this in the sample distribution video, part 1, but what this is saying is that, let's say this is mu, right? If, for instance, we have xn bar and our n is, let's say, 10, right, we're going to have a distribution that looks maybe like that, right, where you can see that it's kind of the middle of the distribution is still mu, but it's got this quite a wide variance or standard deviation. It's quite a wide distribution. But as we're increasing n, what's happening is that it's kind of going closer and closer to n. I mean, going closer and closer to mu. So the mean value is still staying the same. Mu is still staying the same. It's the original mean of our original data, but we're kind of getting closer to it. And then what xn bar, ultimately, what the central limit theorem says about xn bar is that as n goes to infinity, this bottom part is going to go to infinity, and we're going to get something that's a normal with mu 0. So essentially, it's going to be this like very, very sharp peak around mu and like virtually no variation. So in other words, as n goes to infinity, xn bar goes to a particular number, and that's going to be mu, and that's another result called the law of large numbers, but that's not what we're trying to talk about here. What I want to talk about is just xn bar, right? So if we're thinking about xn bar, right, we know what xn bar is equal to. We know that xn bar is equal to the sample average. It's just the average of all of our observations, xi is there. And we can then go and figure out what our sum of all of our observations are equal to. That's just equal to our whatever average we calculated multiplied by n. And that's not difficult to figure out. You just multiply the n, but yeah. So this result over here, I'm sorry, right, xn bar, right, as n goes to infinity, is a normal distribution, is the same thing as saying nxn bar, right, is some normal, where the normal gets multiplied by n and the variance gets multiplied by n. And this is just, I mean, I'm not going to say the proof, because there shouldn't be a proof, but essentially this is because if we multiply by n, that's the same thing as adding up this particular value n times. And if you add up normals multiple times, you're going to add their mu's, or you're going to add their means, and you're going to add their variances. So that's what nxn bar, why nxn bar is also a normal, but you're multiplying each of those things. And now at this point, the n going to infinity makes less sense, because what that means is that mu is going to go to infinity and our variation is going to go to infinity. So now I don't want to really think about the actual limit. I want us to think about it in the sense of approximations. And what I mean by that is that as n gets bigger, this particular value will start to look more like a normal. And we can then substitute in xn bar, and we can, we can see that essentially the sum of our observations, right, as n goes to infinity, and once again, n going to infinity doesn't really make sense, so that's why we talk about approximations. As n gets very, very large, then the sum of our observations will look like a normal distribution with some particular mu and some particular variance. Now, the reason I do that is because we can think of an example, right? We have multiple examples that we can think of where we have the sum of multiple independent pieces of data. For instance, if we had a die, right, and we threw the die, let's say 15 times, right, one single die, we can throw it 15 times, okay? And, well, we're not, okay, sorry, I need to like reiterate something. So in this case, our xi, right, this is, we're throwing a dice once, okay? And this has what's called a uniform discrete random variable or distribution. And all that means is just that xi is equal to 1. The probability of that is the same thing as the probability that xi is equal to 2. That's the same thing as the probability that xi is equal to 6, right? That's just, we're throwing a die. The probability that the number on our die is equal to 1 is just 1/6. The probability that it's equal to 2 is 1/6. The probability that it's equal to 6 is also 1/6. They're all 1/6. So what we can go and do is say, okay, cool. If we didn't know this, for instance, right? We didn't know what this was equal to, or we didn't know that it was equal to 1/6. We can say, okay, cool. We're going to throw a dice multiple times. We're going to throw one die. So essentially, we're sampling right now. N is our sample size, and N is 1 because we're throwing one dice or one die. And we're going to throw it multiple times. We're going to repeatedly sample. We're going to throw the dice once. We're going to see what the number is. We're going to throw it again. We're going to see what the number is. We're going to record all of those. And we're going to throw it multiple times. And we're going to make a histogram of what our data should look like. And if we have this assumption that they are uniform discrete, we should have something that looks like this, where 1, 2, 3, 4, 5, and 6, they should all have roughly the same number of throws, right? We should see a 4 the same number of times that we see a 5, and the same number of times that we see a 6, the same number of times that we see a 3, right? And that's just for one dice. So we can go and do that, and we can see what the histogram looks like, right? Now, if we throw 2 dice, so we're now looking at our n being equal to 2, right? That we can also go and do the calculations for. And it's not a uniform discrete anymore. It doesn't look like a uniform discrete. It looks like something where the probability of throwing a 1 is 0 because you can't get a 1 with 2 dice. The probability of throwing a 12 is 1/6 or 1/36 because that happens, 1/36. That's a double 6 basically, and there's only one double 6. And the most likely value is a 7 because there's so many different ways of throwing a 7. There's a 1 and a 6, there's a 2 and a 5, there's a 3 and a 4, and then obviously the reverse of all of those. Now, we could go and work out all of those probabilities, but we can also go and we can sample that as well. If we didn't know what those probabilities were, we could sample them. We could say, okay, cool, we're taking a sample of 2 dice now, and we're going to go and repeatedly sample this thing, and we're going to go and say, okay, cool, we're going to throw 2 die, we're going to record the number, throw 2 die again, record the number, throw 2 die again, record the number, throw 2 die again, and that's going to have some distribution. And if I make a histogram of the data that I got, that histogram will look like the sampling distribution, or that is the sampling distribution, the empirical sampling distribution, and we can go and do that, and it looks something like that. So we can see that the most likely value we have is 7, right, and that's the most often number. And here in this case, remember mu for this particular thing, for xi, is this particular normal uniform discrete, that the expected value of mu is 3.5. We can go and calculate it. 1 plus up until 6 divided by 6 is 3.5. So when our n is 2, right, when we're sampling with 2 dice, our expected value will be 2 times 3.5, which is 7. And we get that, right? And this kind of looks like a normal. I mean, one important fact is that this particular sampling distribution is discrete and the normal is continuous, so it's not actually a normal distribution, but that's besides the point. And we can go and do it again with 3 dice, and that will also look kind of like a normal. And essentially what the central limit theorem says is that as we go and take more and more and more and more and more and more values, right, or we go and sample bigger and bigger and bigger amounts. Remember, n is our sample size here, so n is the number of dice we have, and the throwing it multiple times is just the repeated sampling to get a histogram. That as you increase your n, your histogram that you get, your distribution that you're going to get is going to look more like a normal. And we can go and see that. We can go and do 4 dice and 5 dice and 6 dice, and that looks very much like a normal distribution. I know my drawing is horrible. And so this is just kind of empirical evidence for the central limit theorem. But the central limit theorem does have a proof, and there is an analytical proof that I will have on my video on my channel, so you can go and check that out. But basically, this is just showing you why the central limit theorem works in the way it does. Yeah, so that's the central limit theorem examples. But now there's this kind of subtle beauty, the central limit theorem, that's kind of very important, or philosophical, I guess, if you want. So this xn bar, right, that's xn bar, we can see that, xn bar, which is you sum up all of your xi's and you divide by n. That the central limit theorem says that as n goes to infinity, that the average of those, that the average of that data will look normal, regardless of what xi, or regardless of what your original distribution looks like. And so the central limit theorem says that as you average the effects, and when I mean effects, I'm saying the value of xi, right? Xi here is basically equal to the effect that you're looking at, right? As you average the effects of a large number of independent, remember that was one of our assumptions, independent factors, the result you get will be normal. Now, this idea or this reasoning can justify why we have so many normal natural phenomena, things like heights and weights, why all of those are normally distributed. And the reason is that you can think of height as being, and I say is, I actually mean you can think it is the result of a large number of factors being averaged out. So essentially, your height isn't determined by one particular thing, it's determined by so many different things. If you think about all of the different genes that you have that kind of contribute to height, you can think about your diet, whether that has an effect on height. You can think about, when you were a baby in the womb, what kind of environment you were in. Was your mother in a stressful environment? Was she in a peaceful environment? Did she eat lots of good food? Was she exercising? Those kinds of things. Your day-to-day environment when you're alive. All of those impact on your final height as an adult, but they're all kind of independent, and central limit theorem does hold for non-independent things as well in a different way, or in a specific, that's like a separate form of the central limit theorem that has its own caveats that you need to go and study if you're interested in it. But essentially, when you think of a particular phenomena as being the averaged effect of multiple independent things, that if all of those things contribute a very small amount, in other words, when n is large, every single the effect that, or the weight that each particular effect has is going to be very small. When you average all of those out, you get something that looks like a normal distribution. And that reasoning extends to many other things in the natural and man-made world, and that's just why that's one of the other reasons why the central limit theorem is so useful and important. But now there's this kind of glaring question about, well, how many samples do we need, or what does our sample size need to be in order for us to use the central limit theorem as an approximation to normal data? So the sample size that we need, or the sample size at which the sample means distribution will look approximately normal. And I say approximately because we can't have an infinite sample. If we have an infinite sample, that either means two things. One, it means we've done something forever, or two, it means that we have the entire population, in which case we're no longer taking a sample, we're taking a population average, and then there's no real point in looking at the sample distribution or the sample means distribution, because then you have the population mean. But anyway, as you get close, as your sample size gets closer and closer and closer, or not closer, larger and larger and larger and larger, as n gets bigger, that your sample means distribution will look approximately normal. And the way in which I'm going to say rate at which your sample means distribution looks normal, will depend on how normal the original data looks. So, for instance, if you have normal data, so if you, for instance, say x1, x2, dot, 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 xn is normal with some mean and sigma squared, right, then it doesn't matter how many samples you take, your sample mean will still be normal, right? That's what we proved in chapter 7.2, is that whenever you take a sample of normally distributed data, that the sample means distribution will be normal. We've proven that before. So if you have data that looks very, very normal, your n doesn't have to be big. It can be any value, whatever you like, and it's going to work. Your sample means distribution will be normal if you already have a normal distribution. If you have what's called a symmetric distribution, right? Symmetric means that you have roughly the same number of values on one side of the mean as you have on the other side of the mean, right? Then, or in other words, your mean and your median are the same, right? If you have a symmetric distribution and you have very little chance of having extreme values, and by extreme values, this can also kind of go on over, right? There's almost zero, there is a zero probability of getting a negative number in a binomial distribution. And if we've got n being 15, there's zero probability of a value larger than 15. So we kind of have this cutoff point where after these particular values, extremes past that are unlikely or impossible. And if you have that case where you have symmetric data and you have unlikely extremes, in other words, your tails, right, are very flat, then n can be approximately 15 to 20. And we saw in the dice example, it can be actually, sometimes it can be smaller than that, depending on what the data looks like. And if you have skew data, right, skew data just means that your median and your mean and your mode are not in the same place. They're kind of either one is greater than the other is greater than the other, or less than the other is less than the other is less than the other. And if you have that case where you have skewed data, but you still have unlikely extremes, in other words, your tails of your distribution, right, the tails go very close to zero because there's very little probability of getting an extreme value, right, then so we sometimes say that n just needs to be greater than 30, and the majority of the time that's the most conservative you'll see our sample sizes being, as long as it's greater than 30. Most people will say you can use the CLT, but once again, that depends on what you're doing with the CLT and how you're making inferences and what kind of inferences you're making and where those decisions are going to be used. And if it's important that you be very, very accurate, then maybe you need more sample sizes. Yeah. And then finally, if you have what's called a heavy tail distribution, which just means that you have this, here's the normal distribution, right? It goes down to zero very, very quickly. Whereas a heavy tail distribution has like this little thing above it where it stays at a certain level, perhaps above, then those are what's known as a heavy tail distribution. And essentially a heavy tail distribution means that the chances of getting a very extreme value, right, a very, very negative value or a very, very, very positive value, those chances are not small. They could be small. Small is relative, but they're not unlikely, as in the likelihood of getting a very, very large observation, right, that actually might happen occasionally. And in that case, you do need a very, very, very large n in order for you to use the central limit theorem. And yeah, that is basically the end of the central limit theorem video. Don't forget to like and subscribe. Yeah, and let me know in the comments if you want to see other videos, what kind of videos you want to see. And yeah, cool beans. Bye.